Hello everyone, welcome back. I want to move along into chapter 4. We're now talking about continuous random variables rather than the discrete. The Poisson distribution is the last of the discrete stuff for us. I want to make a couple of announcements for those who are wondering what you'll have to do next. There will be a homework number 8, so a written homework 8 will be due next Friday. I will post that by this Friday, and it'll include some stuff about the Poisson distribution. I want you to work with that a little bit, and a little bit of stuff from what we'll talk about today. Also, I moved the WebAssign to also be due next Friday. What day is that? That will be April 10th. So you'll have a couple of assignments due at the end of next week. Anyway, let's move on and talk about these continuous distributions because our setting has changed quite a bit. So a continuous random variable takes values on some interval of the real number line. Now this is quite a bit different because before we just had some list for the discrete stuff. A list of possible values. So this changes things quite a bit. So let's say big difference. Now our probability function which we also call the probability distribution, is a probability density function. Which we'll shorthand as PDF. This is a big difference from what we had before. Before, for the discrete stuff, we called it a probability mass function. Mass function, which we referred to as the PMF. And so we changed the terminology a little bit. Now, so instead of a probability mass function, which we were calling our little p of x function, where each p of a particular value is a probability. And actually, in particular, it's the probability that random variable takes that value. Instead of that, the best we can do is what we call a probability density function, which we're going to switch, and instead of calling it little p of x, I'm going to match the book's convention, and we're going to start calling it little f of x. And I don't think there's any real reason for that other than it looks more like the calculus we're used to. And we can find probabilities that my x takes some value between a range of numbers. So I can't get the probability that x takes some particular number. That would actually be a probability 0. And so let's think about why that is. So now I have a random variable, and it can take all the numbers in some range of the real number line. And how likely it is to take numbers somewhere depends on how high up some function is. However, at a particular value, let's say little a, there's no thickness here. My probability of taking that exact value has to be 0 for any of this to make sense, because, well, I couldn't have a positive probability for all these numbers. Even if I'm shrinking down really fast, it's not like with the discrete stuff with our negative binomial or things like that, where the larger and larger numbers got smaller enough where we still had probabilities that made sense. So instead, the best we can do is say, okay, well, what's the probability I take a value between some number and some other number? In other words, what's the probability I take a value in here? Now we can work with these heights, these densities of how high up is this at these numbers in between, and, oh, I want the area in between. So before, when we wanted probabilities for some range of numbers, we had to add them up. We had to take some sum. We would say, what's the probability of taking this value plus all the ones in between up to the probability of taking this value? Except we can't do that because all these numbers would have to be 0 now. And also I can't add up this whole real number line's worth of stuff. You can't do that. So we need a different kind of sum. I mean, I guess I could chunk up the space and sort of estimate and say, okay, well, all the ones that land in here, we just say take this value, and all the ones that land in here, we say take this value. But then what you're doing is you would just be approximating and taking some sort of partial sum, and you wouldn't get exact answers. So instead you would need to limit that off, and what you end up doing, because we can't do that, is you need a fancy sum, and we use that fancy S for fancy sums. And so then what ends up happening is that if I want the probability of landing in that range, I just integrate that density function, and that tells me that answer. Now again, there's no thickness above any particular number. That would just be some line here. So it doesn't actually matter if this is less than or equal to or just less thans. It won't really matter. These would all be the same number. If it's like that or like that or like that, it would be the same answer. And so to calculate probabilities for continuous random variables, we can just do probabilities of landing in some range here, and we do it by integrating. And that's really the only change to the setting. We still have rules. Very basic rules of probability all still apply. If my density function looks like this, the area underneath everything, in other words, we still need, and now we'll denote this, the integral from negative infinity to infinity. In other words, over all the possible real numbers for this density function has to equal 1, because the probability of something happening is 1. We still need that always. Which this leads me to one question that's in your homework that I want to go ahead and do for you. So as an example, because I thought this was a bit tricky, so let's say WebAssign homework 10. Question number, I believe this was, let's find it. Question number 5. And I just want to talk about part A for the moment. It gives you, so we're given that our probability function is defined as some number k, which it doesn't tell us, over x to the 7 whenever my x's are bigger than 1, and 0 whenever my x's are less than or equal to 1. And so this is a bit strange, because if I want to integrate here, this is valid for everything greater than 1, which means off forever to infinity. And the first question it asks is, for what k is this a probability function? And so this is maybe a little more of a Cal 2 thing, which is why I wanted to go ahead and just do it together. And you can refer back to this when you have to do it later. So what we're going to end up needing to do is, well, what's the rule to be a valid probability function? We need the integral over all the stuff from all the way off to the left to all the way off to the right to be 1. And so, well, first off, if I want to take the integral from everything off to the left to everything off to the right of this function, I can immediately simplify this problem a little bit, because this thing equals 0 up until I get to 1. So I can just say, well, this is just the integral starting at 1 to infinity, because everything to the left of 1 isn't going to do anything. And okay, let's plug in our actual function there. So we want the integral from 1 to infinity of k over x to the 7. Now, how do I do an integral that goes off forever? That's a bit of a tricky thing. So if you have your function, and maybe it starts somewhere, and it goes off forever, how do you do the integral all the way on forever? And the trick is, you do the integral up to some number, let's call it little t, and you calculate those, and then you just take the limit as your t's get bigger. So you let your t's get bigger, and you'll take the limit of those integrals that take part of the area that just gets a little bit bigger as t gets bigger. And so let's do that really quick, because we'll use that same trick to derive some things later. And so this is going to be the limit as t gets bigger of the integral from 1 to t of this function. Okay, so now we need an antiderivative for x to the 7. So this is going to be, what's my antiderivative? Not x to the 7, sorry, 1 over x to the 7, which is x to the minus 7. What's an antiderivative for that? Well, I'd go up 1 in the power and then divide by that 1 higher power, so that would be x to the minus 6 divided by negative 6. And now I still have that k on there. So, all right, so we have limit as t goes to infinity, and now this is going to become, the antiderivative was, I had a minus pop out, the k is still going to be on there, and I'm going to have x to the minus 6, which I can just write as x to the 6 on the bottom, and then also a 6 came out on the bottom. So we have a 6x to the 6 on the bottom. And we're integrating from 1 to this placeholder t that we came up with. And so finally, we're looking at the limit as t goes to infinity of, what is this going to become? Well, we'll plug t in, so minus k over 6 t to the 6th minus, what do I get when I plug in the 1? So that would be, we have minus k, so this would become plus k over, now if I plug 1 into 6x to the 6th, that's just going to be 6. And so I want the limit as t goes to infinity of this thing. But that's pretty easy because if t is getting bigger and bigger, this term is just disappearing. It's going to get smaller and smaller, so we're ending up getting k over 6. And so for this to have been a legitimate probability function, we need that k over 6 to equal 1. Hence, k must have been 6. And so that answers this kind of question. For what k is the probability, is this a probability function, following that rule that the integral over everything has to be 1, because the probability of anything happening is 100% or 1. Now that question goes on and has you do some things with the cumulative distribution function and such, and we'll come back to that in the next video. For now, I want to move on and talk about one particular distribution. We're going to do some named ones, just like we did for the discrete stuff, and that will be the uniform distribution. So the uniform distribution, the idea is my random variable is just everything has the same density above it. Now that means I can't take values all across the whole number line, because then the area underneath wouldn't be 1. So we need some fixed range here. So it's only going to work if I'm between, say, some number a and some number b. I'm going to follow the book's notation here. And my function is just going to be flat. My density around all the numbers is going to be the same, which means my actual density function has to be 0 everywhere else. And maybe we just say it jumps here like this. Again, what it does along any particular slice doesn't really affect anything. So you could have put the 0 down here and have it jump up here, and it wouldn't really change anything. Oop. So what does a uniform distribution do? The uniform distribution says that our probability function, or our probability density function, is of the form it takes some value that's going to be the same across that range, so that will be for all my x's between those two numbers, and 0, let's just say elsewhere. Now, what is the number that goes here? Well, if I need this to be flat, the area under the entire function is actually just going to be the area of this rectangle. In other words, I would need the length of this, which would just be b minus a, right, times this height. So I would need b minus a times this height to equal 1, which means that that height is just 1 over b minus a. So for a uniform distribution, my probability function over that interval is just going to be 1 over b minus a. Now, we call other things uniform distributions. You could say everything's equally likely in terms of density on this square. And let's say it's a unit square. So if I put it on a graph, this would be 1 and this would be 1. And now let's say my random variable is actually just points in that square. Okay, well, if I gave my probability function over this two-dimensional thing a height of 1, then that would all be equally likely. It wouldn't really be area underneath, it'd be volume underneath, but it would be 1. And then I would really just want to say, what's the area of this region? And that would give me the probability of my random point landing in that region if it was uniform. So this sort of probability distribution does apply to more interesting cases than just intervals on the number line. But for our purposes, we're just going to focus on intervals on the number line because it's a pretty good introduction to the idea. Okay, so the next question is, if I have a uniform distribution, uniform distribution. So let's lay down the rules a little more clearly for it. The probability function takes these positive values, which have to be this, for the x's that are actually in that interval between a and b. Zeros elsewhere. And then the next natural questions are, what's my expected value? And what's my variance? So let's work that out really quick. We'll talk maybe more about it later, but the first idea is that our expected value and variance, the calculations follow the same rules, except instead of these discrete sums, we're doing fancy sums. That's the only difference. So if I want an expected value, I still add up, except now fancy sums, so integrate over the entire range, but remember, this negative infinity to infinity, it's going to be 0 except for on that interval from b to a, or a to b, sorry. So that'll simplify for us. But anyway, to do an expected value, I would just add up, and it's the value taken times the probability there, except we don't have probabilities there, we just have the density there. And so if I want to compute expected values, it's still this. I just have these fancy sums now. And now for this example, the uniform distribution, this isn't too bad to do. We just get, okay, it's going to be 0 everywhere, so my integral will simplify to go from a to b of, well, what value is this f of x? For all those places where it is not 0, that's just going to be 1 over b minus a, and then we still have this x here. So we're going to end up with x over b minus a. And so this is the expected value. Let's calculate what that is really quick. An antiderivative for x over b minus a, well, that b minus a will still be on the bottom. And what's going to happen to that x? It'll go up a power, and then I'll divide by the higher power, so we'll get an x squared, but then we end up having to divide by 2, so this b minus a on the bottom will get doubled. And we're integrating from a to b, of course. So this is going to become b squared over 2b minus a minus a squared over 2b minus a. And now this simplifies quite a bit because I have a common denominator. Let's put that together. So this is going to be over 2b minus a. And now I have b squared minus a squared. That's a difference of squares. So this will actually factor as b plus a, b minus a. And then we're in luck. The b minus a's cancel. And so we get that b plus a and then over 2. And let's clean that up a little bit. Let's write it as a plus b over 2. And so that's our expected value. And so let's look up here. We found this expected value. It's a plus b over 2. And let's take a look for a second because this should have matched our intuition extremely well. And let's see why that is. If I look back at what the density function here, the probability function actually looks like for our uniform, it's this flat rectangle, right? Where the density, or the likelihood, is all the same all through here. And so the expected value, which is just an average value taken, happens to be, well, what is a plus b over 2? That would be the midpoint. So a plus b over 2 is just the middle value. And so all things being equally likely, our expected value is just the middle value, which is what we should have expected. Okay, now for something a little different, let's try our hands at the variance. Now, to make a little bit of a jump, all of the rules, algebra-wise, that we can follow, pulling numbers out of the sums, breaking the sums up over addition or subtraction, things like this. That basic algebra is still true for our fancy sums. I can still do it with integrals. And so we can derive the same, what we call the shortcut formula for variance. And so if I want the variance, I can still think of it as, expected value of x squared minus expected value of x all squared. That's still going to be true. I can take the variance formula written in the more, by the definition, direct way, except I have the integral now, the fancy sum, instead of the sigma, the regular sum. But then I can rearrange it in the same way and still get here. And so we just want expected value of x squared really quick. So let's find that. So expected value of x squared is going to be integrate over everything of x squared times the probability function, which in this case, since this is 0 outside of that interval from a to b, I really only need to integrate from a to b, and then I'll have x squared and then times 1 over that b minus a, because 1 over b minus a is what this f of x spits out in all the places that matters. Okay, let's do this integral really quick. So that's going to be, what do I do with this x squared? This power is going to go up, and then I'm going to divide by that higher power. So we'll get x cubed divided by 3, but I still got that b minus a on the bottom. And this is going to be, we integrated from a to b. So this will become, plug in the b, so b cubed over 3 times b minus a minus a cubed over 3 times b minus a. And so I've got b cubed minus a cubed over 3 times b minus a. Now, this should simplify. However, how do I factor b cubed minus a cubed? And no, it is not b minus a cubed. This is bad. You can't do that. So we need a little bit of a trick here. So on to this, as a side note here, let's just, let's write what this trick is. This is for a difference of cubes, things cubed, b cubed minus a cubed. The factoring trick we have is that if I have a difference of cubed things, I actually can pull out that b minus a, and then what's going to remain is a b squared, capital B, sorry, a b squared plus an ab plus an a squared. If you don't believe me, we can just check that multiplication really quick. If I have b minus a times b squared plus ab plus a squared, and now let's just do this multiplication. B times b squared will give me a b cubed, b times ab will give me an ab squared, b times a squared will be a squared b, minus a times b squared will be minus ab squared, minus a times ab would be minus a squared b, and then minus a times a squared would be minus a cubed. And then what's happened for us is my ab squared here cancels with the minus ab squared, the a squared b cancels with the minus a squared b, and then what's left is just b cubed minus a cubed. And so yeah, this formula works nicely for us. So with that in mind, let's go back to where we were. That b cubed minus a cubed on top of this fraction here will factor. And we've got b minus a times b squared plus ab plus a squared squared. And this is still over 3 times b minus a. And now my b minus a cancels. And so we've got b squared plus ab plus a squared over 3. Now, remember, this is just expected value of x squared. We haven't found the variance yet. I make that mistake a lot in class, as you all probably know. So, let's get that variance really quick. Our variance is expected value of x squared minus expected value of x squared. And now we found the expected value of x squared. That was b squared plus ab plus a squared over 3. And then I want to minus, my expected value of x was a plus b over 2. It was just that midpoint squared. And so we have a little bit of work to do. Let's leave the left here alone. And now let's square the thing on the right. If I squared a plus b, what do I get? I get a squared plus 2ab plus b squared. And I square that 2 on the bottom, I'm going to get a 4. And now I don't have a common denominator. We're going to need to get that, and then we can bring the fractions together. So I'm going to get something over 12. Now all the stuff over here would have needed to get multiplied by 4. So we're going to have 4b squared plus 4ab plus 4a squared. 4a squared. And then minus all the stuff over here, which would need to get multiplied by a 3. So let's see what goes there. So we'd get minus 3a squared minus 3 times 2, so minus 6ab, and then minus 3b squared. And now we have a little bit of cleaning up to do. I've got 4b squared minus 3b squared. So we've got just a b squared left. I've got 4ab minus 6ab. So we've got minus 2ab. And then I've got 4a squared minus 3a squared, so we're going to get plus an a squared. And this is still all over 12. And now this actually worked out pretty nice for us because that top there will refactor. That's just b minus a squared. And then we still have the 12 on the bottom. So there's our variance. So going back up to our list of formulas, way back up, we finally have that variance where it's the length of that interval squared divided by 12. So there's our formulas for uniform distribution. Anyway, y'all, I think that's a good place to stop for this lesson. I'll post another video tomorrow finishing up section 4.2 and maybe doing a little bit more homework examples for y'all. Thank you.